Welcome to the 12th video of this course on quantum processing. Last time we talked about the quantum error detection using the orthogonal and non-orthogonal states of the corresponding error operators, the cross operators that we had. Today is about the Shor's 9-qubit code, and this is a nice code that you will see for correcting arbitrarily single qubit errors, and you'll see also that it works for even 2-qubit errors. It was invented by Shor, Peter Shor, who was a pioneer in this field in 1995, as you see. And 9-qubit code consists of the following: that you have the logical zeros, and you have triplet states, superposition state tensored 3 times, as you see, for the logical zero. And for the logical one, you have the triplet state, but just in the minus sign, difference minus sign, and also it's tensored 3 times, as you see. This code works like the following. If I would like to expand the state, each state, let's take the first logical 0 and expand it like this. You have kind of tensor product state, and when I would like to apply what I learned for the syndrome and the recovery operators, I will choose the following syndrome operators for this code. They are 6-bit flip codes, 6-bit flip checkers, and those checkers will work as the following. I have Z1, Z2 that will play with this first and the second sections of this triplet. And for the Z2 and 3 will be on the second and the third of this triplet, and also for 1, as you see. Okay. For the Z4 and Z5, they will work on the second tensor here. So for the 4 and 5, and the 5 and 6 here, also for 1s, and the Z7, Z8, the first 2 of this triplet here, they are number 7, degrees number 7 if you count, and for the 8 and 9, the last 2 of this triplet. So these kinds of checkers or operators that we have, the syndrome operators measurements that we have here, are called for parity check operators for bits. So these are parity check operators for bit flips. Okay, this is for logical zeros, or the first logical zero that we have. What about the second one? We will employ 2 kinds of phase flip checkers that we have here, from x1 to x6 counting, and we will repeat for x4 until x9 to match the condition for this code. Those are parity check operators for phase flips. Okay, and they will also show us that they are good for bit flipping also, phase flip. And those are what we call the checkers or parity checkers for the phase flip. So let me tell you how it works, like affecting the state of this qubit, checking the state for this qubit for phase flipping, but from the perspectives of the some metrics that we would like to define, is that the number of errors that we have in this kind of codes, and or any codes that we would like to measure the errors in, works like the following: that I have the identity, which is just single, so it's called identist 1 for errors, and the n, so the n here are the kind of triplet. Here we have 3, so the n will be 3, so if I count carefully, plus 1 plus 3, and q, the number of qubits that we have, are 9. So there are possible 28 errors that can happen for this case of the triplet case here. And these are actually 28 errors, but they are also 28 single qubit errors, though they are characterized for single qubit errors. If I have to go again and check that what I said for bit flipping and the phase flipping operators, syndrome operators that I have, we will actually have that the number of syndrome values, syndrome measurements that we operated on the system have corresponding errors that are actually 1, 2, 3, 4, 5, 6 bit flippers or bit flip checkers, and we have 1, 2 kinds of phase flippers here. So the number of value syndrome measurements or syndrome operators values are going to be 6 and they're 2, so 2 raised or 2 power 8, and the 2 power 8 are the 2, 5, 6, 256 possible errors. And those from the distinguished or distinguishable syndrome distinguishable syndrome errors that we have. And if you look here carefully, that there are 256 and here 28 errors, and it means that I have complete number of degrees of freedom for the errors that I have when I apply such flip or parity flip checkers, or even parity phase bit and phase flip checkers that we have here. And these confirm the idea that the Shor's 9-qubit algorithm is a good idea for correcting errors. So it's a perfect quantum error detector. So it can correct for, as you see, that there are even huge number of errors that we have in the system, that this kind of qubit or kind of code that we have can correct them carefully. Let us go to say that the 9-qubit approach by Shor is beautiful, and even it's not only for single qubit errors as you see, but they are also kind of 2-qubit error correctors. Let me flip this and go to another page, and this page is what is actually the perfect quantum codes to identify. The answer will be identified when I try first to remind you that the quantum codes, okay, which consists of the case subspace vector of this Hilbert space and qubit case, are with just neglecting the Hamming distance for a second, and say that this n and k have number of syndrome operators that are going to be like this. You have the log base for the 1, 3, n. So for the this formula just here, okay, number of syndrome operators. Okay. So let's answer the question that we asked here, raised here. What's the perfect quantum code? It's actually the 5-qubit case. Why it's 5-qubit case? This is the answer, and we would like to know the reason for this. If I apply the number of errors that I have here, that if you just go to this and remind yourself that the number of errors go to be like this. So let's just flip it and say that I have for this is 1, sorry, here, 1 plus, I have 9, I have 5, okay, just 5 times 3, because I have triplets, okay, and this is nothing else than 16 possible errors. If I apply the syndrome measurements, the syndrome operators, I will find that there are actually log 2 raised to, I have here 3, here just 5, okay, because I have 5-qubit case, so I have 16, which is about 4, and 4 are the number of syndrome operators. Okay, look carefully. We have 16 errors, and we have the number of errors that I have for distinguishable errors will go as 2 raised to 4. This is actually 16 possible distinguished or distinguishable errors. Really? Yes, this is true, because I have the 16 errors which also coincide with the 16 errors that I got from this measurement, and this is exactly the distinguishable errors, or actually equivalent to the number of possible single qubit errors that I have, which means that this 5 qubit case is excellent and perfect for error detection and for error correction also. I recommend that you go for this nice book by Simon Davidson, the quantum error correctors or quantum error corrections for beginners. It has a very nice illustration for the Shor qubit in terms of a quantum circuit for this Shor 9 qubit case that it mentioned in their book. Thanks a lot for watching, and see you in the next video.